You all can hear me, right? Making sure someone could say yes in the chat. Can you hear me? I just asked if you could hear me. Cool. Thanks. All right. Excuse me. Oh, all right. Yeah, let's see here. Okay. What's up? Well, thank you so much. You're very kind. Um, the it was a special day, an anchor day. 6/6, like 8/8, 10/10, 12/12, all on a Thursday this year. And on an anchor day. All right. So today we're mostly going to talk about powers of matrices, the stuff you talked about in Liddell's and the other teacher's class yesterday. Before we get going, two things I want to mention. Thing one, on Canvas, if I can get up here, sure. So if you look at our Canvas, you might have already noticed and done the evaluation that is like right at the top there. If you haven't already done that, please do it before the end of the quarter. I would appreciate it. Yeah, we're definitely going to talk about the AP equals DP stuff. Yeah. And then the other thing that I just posted this morning was a final review. We are going to have a final review next week. We can either do it Tuesday or Thursday. If you care what day it is, comment on, let's see, people have already said Tuesday, Wednesday. So if you care what day, go write just one time for each person, what day you would prefer, and we'll choose a day. If it doesn't happen to be a day where you can come, it's going to get recorded and posted. So that's why my preference is probably for Tuesday, because that gives you more time to see it, right? Because your final's on Thursday. So if it were up to me, I mean, if I was not taking your feedback, I would just pick Tuesday. But if everyone overwhelmingly would prefer Wednesday, then we'll do Wednesday. So go do that before the end of business day today. That's all I've got as far as things like that. Let's go ahead and jump right in. So I'm going to start us off with an example because I think it's a good example to kind of demonstrate what we're doing with this iterated matrix multiplication, where you're just taking a 2x2, really could be any square matrix, but in this class is going to be a 2x2 matrix raised to a higher power, often then multiplied by some vector. So here is the setup. By the way, most of the things I've been doing in this class, in case you didn't already know, are handouts that are on Grant's webpage. So if you want like the notes for this, you can go look at Grant's webpage and see them. Like they're nicely written out, but not that you shouldn't pay attention. Just they're there for you later if you want to see them. Also plus minus, of course. So here's the setup. Suppose we are studying a population divided into two age classes. Juveniles and adults. Juveniles have an average of 2 offspring, while adults have an average of 6. %50 of juveniles move on to become adults. The Leslie matrix for this is something you should all be able to come up with. We're going to just write it out. That describes this is the following. The matrix is 2, 6, right? So each juvenile produces 2 offspring, each adult produces 6 offspring, and then 50% of the juveniles move on to adulthood. And we didn't really say it, but we're going to say like after adulthood, you just die. Okay. I know it's not very uplifting, but such is the math of the Leslie matrix. So what we want to eventually be able to do here is say like how many, if we start off with some initial population. So in fact, so if we are given an initial population of, I'm going to write this as n naught, which will be the vector j naught, a naught, j naught for the initial number of juveniles, a naught for the initial number of adults, equal to 100 for the juveniles and 80 for the adults. What we really want, the big question that we're going to try to answer is, how many adults and juveniles will there be after 20 population time iterations, right? You could think of years or weeks or whatever. Basically, every 20 generations is probably the best way to say that. Excuse me. So we can certainly find the population at different times or generations. Let's say times. So here's the idea. So if time equals, if we have 1 generation later, we would just multiply our initial population by the Leslie matrix. That's going to be, let me write this well. It's going to be n1 equal to a times n naught. So let's actually calculate that. That's going to be the matrix 2, 6, 1/2, 0, multiplied by the initial population vector 180. And that's going to be 2 times 100 plus 6 times 80. So that's going to be 200 plus 480, so 680. And then 1/2 times 100 plus 0 times 80. So that's how many juveniles we have after 1 generation and adults we have after 1 generation. And we can keep doing this, although it gets a bit tedious the further you go, right? If time was equal to 2 generations later, our n2. So I don't want to like do too much work here. I should just say that the next one's going to be a times the previous one, right? Because every generation, all these new juveniles and adults, all 680 of these juveniles are going to produce two new juveniles. All 50 of these adults are going to produce 6 new juveniles, and then half of these juveniles are going to make it to adulthood. So we're going to get the same matrix, 2, 6, 1/2, 0, multiplied by n1, which is 680, 50. So then 2 times 680 plus 6 times 50 is something. What? It's going to be 14, 1360 plus 300 is 1660. Yeah, that's right. And half of 680 is 340. And that's the number of juveniles after 2 iterations and the number of adults after 2 iterations. Notably here, I will point out that N2 is equal to A times N1, but N1 is really equal to A times N naught. This is equal to A times N naught, which is equal to A squared times the initial population of juveniles and adults. And the idea here is essentially that every time you want to find the next generation's values for juveniles and adults, whatever the vector is, you're just going to multiply that vector by the Leslie matrix that many times. So we could say more generally that the number of juveniles and adults after T generations or iterations is going to be A raised to the T power times your initial population vector. And unfortunately, multiplying a matrix by itself is kind of gross. It gets complicated the more times you do it. So fortunately, there's a way to make it somewhat easier. Kind of easier. Yeah, easier is probably the right way to say it. So here is where we're going to go back a little bit. So we know, don't worry, we're not done with this example, but we're going to say for our 2 by 2 matrix, or for some 2 by 2 matrix A, we have eigenvalues and eigenvectors. And although it's not always true that you get 2 eigenvalues and 2 distinct eigenvectors, it's gonna always be true for us. So we have eigenvalues. By the way, you should interject with questions if you have them, obviously. Like, just want to make it clear, right? You can stop me. I can say more words about things. And we have eigenvalues, lambda 1 and lambda 2 with associated eigenvectors. V1 and V2. So what we're going to do is we're going to make a new matrix. We're going to call it P typically. And P is going to be the matrix where the columns are the eigenvectors of A. And the order matters, but you can pick any order you want, as long as you make sure you're paying attention. Meaning you can either write P as the first eigenvector as the first column, and the second eigenvector as the second column, or you could switch them. And if you switch it, if you write them in the other order, it just means that the diagonal matrix we're eventually going to get, the eigenvalues have to be in the same corresponding order, which we'll see in a minute here. All right, so here's what's true. The matrix A times P is going to equal P times D. Okay, that seems maybe like not super obvious from the get-go. So let's actually say more about that. So if I write it out this longer way, what I really have is the matrix A, which we're still going to write as A, times the V1, V2, that's your P right there. We write these little dashes here just to indicate that it's like taking up the whole column. There's your P. And that's going to equal the same matrix P times the, interesting. Yeah, sure. Times the matrix D, where D is the matrix of eigenvalues in the same order on the diagonals. So it's lambda 1, 0, 0, lambda 2. So here's what this says, although it might not be super duper obvious. If you multiply these two things together, what you really just get is lambda 1 times your first vector as your first column, and lambda 2 times your second vector as your second column. And if you multiply these two things together, what you get as your first column is A times your first eigenvector and A times your second eigenvector. So all we're saying is something we've said before, which is that A times the eigenvector equals lambda times the eigenvector, and A times the eigenvector equals the other lambda times the eigenvector. So that's where this is all coming from. The fact that A times any eigenvector is just equal to the eigenvalue times that same eigenvector. So that's what makes this equation true, that A times P equals P times D. So again, all we're getting is A times P equals P times D. P is the very good question. Let me actually write the words. So P is the matrix whose columns are the eigenvectors of A. So as you can see, or maybe you can guess, the process of doing what we're about to do is going to take a little bit of work, because we're going to have to find the eigenvalues and the eigenvectors and write the matrix P, and then also find the inverse of P. So it's a little bit, it's kind of a few pieces to this thing. So wrapping this part up, I'm going to isolate A by multiplying both sides on the right by P inverse. P has to be invertible because reasons. So A times P inverse is equal to P times D times P inverse. I'm just taking this equation, multiplying both sides on the right side. You have to do the multiplication by matrix on the same side for each part of the equation. And then A times P inverse, well, P times P inverse is just the identity. And A times the identity is just A. So we get A equal to P times D times P inverse. Now, what's special about this is that now we can raise A to a higher power, and the calculation is not terrible. Let's explore this for just one more minute, and then we'll get back to the example, I promise. So here's the idea. Come on. So if we have A equal to P times D times P inverse, then A squared, which is just A times A, that's going to be PDP inverse times PDP inverse. But notably, you can do any two matrices multiplied together first, right? You can do either P times D or D times P inverse or P inverse times P or P times, right? It doesn't matter kind of which ones you do first. You just can't change the order, right? You have to leave them in the same order. But we can specifically write this as P times D times P inverse times P times D times P inverse. P inverse times P, that's the identity again. So, and then D times the identity is just D. So what we really end up with is P times D, which is D squared times P inverse. Let's do one more just to kind of see it. So if you look at A cubed would be A squared times A. A squared already simplified to that. So it's P times D squared times P inverse. There's your A squared times P times D times P inverse. There's your A. But look, the same thing happens again. The P inverse times P is the identity. And then whatever you multiply by the identity is just itself. So you get D squared times the identity times D, which is going to come out to be D cubed in the middle. So you get P times D cubed times P inverse. I think we can kind of see that this pattern is going to continue. So what's going to happen here is that A raised to any power, I should be more specific, A raised to any positive integer power, right? The power should be a positive integer because we don't do matrix multiplication with fractional powers. So A raised to the tth power is going to be P times D to the T times P inverse. And you might be thinking, well, that still doesn't seem better because you have to still find D raised to a power, but diagonal matrices are special. So note, D raised to the tth power D is a diagonal matrix. It's usually just the eigenvalues. If you take a diagonal matrix and you multiply it by itself, look what happens. D squared is lambda 1, 0, 0, lambda 2 times lambda 1, 0, 0, lambda 2. And when you do this matrix multiplication, you get lambda 1 times lambda 1 plus 0 times 0. That's lambda 1 squared. You get lambda 1 times 0 plus 0 times lambda 2. That's 0. You get 0 times lambda 1 plus lambda 2 times 0. That's also 0. And you get 0 times 0 plus lambda 2 times lambda 2. That is a lambda 2 squared down there, and 0 is up there. And that pattern also holds. If you multiply it by itself again, D cubed would be lambda 1 cubed, 0, 0, lambda 2 cubed. So when you raise a diagonal matrix, which is the matrix where there's zeros everywhere except for on the diagonal, you just get each diagonal entry raised to that power, which is beautiful. So D to the T power is just the entry in the 1, 1 position raised to the T power, and the entry in the 2, 2 position raised to the T power. And everything else that's off diagonal is still 0. Great. So back to kind of the problem we were talking about, what we're going to see here is that the number of juveniles and adults after T iterations of this process, which we said was a to the T times n naught, we can now make a better calculation, say it's going to be P times D to the T times P inverse times n naught. And that is how we typically go about calculating this sort of thing. So we're going to go back to the actual example now, but I should pause and see, are there questions so far? Okay. Obviously, you're always welcome to ask questions. Just going to take a break for a sip of water. So back to our example. Our Leslie matrix was A equal to 2, 6, 1/2, 0. And our n naught was, how is this better? The way it's better is that A to the T is terrible to calculate. D raised to the T power is easy to calculate. That is what is better about it. The diagonal matrix raised to the T power is much, much, much easier to deal with than A raised to a high power. That's how. Our n naught was 100, 80. And we'll see in this example how it's better. Yeah, so we have to find all the things. And so let's actually ask a question before we say it. Suppose we want to find N10, the population after 10 iterations. So the population at T equal to 10. So what we're going to end up finding is N sub 10 equal to P times our diagonal matrix to the 10th power times P inverse times N naught. So we have to now find the eigenvalues and the eigenvectors. Unfortunately, this matrix is not one of the really, really nice ones where it's upper triangular or lower triangular, because if it was, the diagonal entries would just be the eigenvalues. So just as a quick aside here, just so everyone knows this, right? If your matrix is something like 2, 0, 5, 7, or 2, 13, 0, 7, both of these matrices have eigenvalues that are 2. Oh, sorry, can't quite see that. Both of these matrices have eigenvalues that are 2 and 7. Because if you have a 0 here or a 0 here, the eigenvalues are just the diagonal entries. I made them the same just so I could write that they were the same, but they wouldn't have to be the same. So if you see a matrix like that, you can kind of skip the calculating of the eigenvalues because they're right there for you. Here, not the case. So we're going to find the eigenvalues. So eigenvalues, if you're being asked to find eigenvalues, you're just going to immediately start with determinant of A minus lambda times the identity matrix equals 0. You shouldn't write that all. I mean, you shouldn't write out like A minus lambda times I. You should really just take your matrix A and subtract lambda from each of the diagonal spots. So that's going to become the determinant of 2 minus lambda 6, 1/2, 0 minus lambda equal to 0. Just subtract lambda from each diagonal spot and then do the calculation. So taking the determinant of this, it's going to be the product of the diagonals. So 2 minus lambda times 0 minus lambda, let's just write negative lambda, minus the product of the off diagonals. 6 times 1/2 equals 0. The hope is always that this factors. It might not factor, but I would be really surprised if it didn't factor on an exam. So then we're going to multiply this out. Negative lambda times negative lambda is lambda squared. 2 times negative lambda is minus 2 lambda. Negative 6 times 1/2 is minus 3 equal to 0. And this certainly does factor as lambda minus 3 times lambda plus 1 equal to 0. So we got two eigenvalues. So we're going to say that lambda 1 is equal to positive 3, and the lambda 2 is equal to negative 1. Those are our eigenvalues. And now we're going to find the eigenvectors. I would always choose to find the eigenvectors by solving a times v equal to lambda times v. So we're trying to solve a times the unknown v equal to 3 times the unknown v, which is going to be 2, 6, 1/2, 0 times the eigenvector that we're trying to find equal to 3 times the eigenvector that we're trying to find. Most of the time, you only need to use the first equation here. So using the first equation, we get 2 times x plus 6 times y equals 3 times x. Just to point out, if you use the other equation would be 1/2 times x plus 0 times y equals 3 times y. But I use the first one because I always use the first one. So that's going to be 6y equal to 1x. And when you have nice integer coefficients like this, the easiest thing to do is to say your eigenvector is the x value is the coefficient of y, the y value is the coefficient of x. Because literally, if you plug in 6 for x and 1 for y, 6 times 1 equals 1 times 6. Done. You can make a different choice. You could pick 12 and 2, negative 18 and negative 3, whatever you like, but the normal standard choice is smallest integer values that don't involve fractions. Okay, let's do it for negative 1 as well. So for lambda equal to negative 1, we're trying to solve 2, 6, 1/2, 0 times, again, the unknown eigenvector that we're trying to find equal to negative 1 times the unknown eigenvector that we're trying to find. So we're going to get 2 times x plus 6 times y equals negative x. Hold on to that thought. We'll come back around to that in just a second. So solving this, we get 6x equal to negative 6y, apologies, equal to negative 3x. I would reduce both sides of this equation. Like if you can divide by a common factor like 3 here, we should, to say that 2y equals negative x. So then my eigenvector here, I'm going to pick x equal to 2, y equal to negative 1. It would be just as good to pick negative 2, positive 1 if you wanted to. Either way is totally fine. And if you make a different choice to someone else, your answer is going to look a tiny bit different, but not different enough that it matters. Somebody asked, what about the other equation in this either matrix? Aren't the two equations we have to solve for? And the answer is actually no. The other equation will give us the same eigenvector. So if we look at the other equation here, the other equation would have been 1/2 times x plus 0 times y equals 3 times y. But then if you multiply both sides of this equation by 2, you get x equal to 6y, which is exactly the same equation as that. So it really, really doesn't matter which of the two equations you use, and you only need to use one of them. There are rare exceptions. Sometimes, so the rare exceptions usually happen if your original matrix was upper or lower triangular. And when that happens, usually for one of the eigenvalues, you'll end up getting one of your equations will be like 3x equals 3x, which doesn't tell you anything. And then you do have to use the other equation. So if you have an equation like 2x equals 2x or 5y equals 5y, that doesn't really tell you anything because that's always true no matter what y is, then you do need to use the other equation. but that's kind of the exception, not the rule. Okay. So we found the eigenvalues, we found the eigenvectors. Now we're going to make the matrix P. It doesn't matter which order you pick, but try to be consistent. So I'm going to use V1 and V2. So we're going to say that P is equal to 6, 1, 2, -1. And I'm reading that in the wrong way I usually read it. So I'm reading it as columns. So P, the first column is 6, 1. The second column is 2, -1. And even though you don't need to at this moment, but we might as well go ahead and say that we know that D is going to be the diagonal matrix, where the eigenvalues are the diagonal entries, and they have to be in the same order. So since the first eigenvector in P was V1, the first eigenvalue has to be lambda 1, which was 3. Similarly, since the second eigenvector was V2, the second eigenvalue, or the column with the second eigenvalue, has to be the eigenvalue lambda 2. That is always true in this process. And then we got to find P inverse. The P inverse is not too bad. P inverse is going to be 1 over the determinant of P. And then you're going to do the usual thing for a 2x2. You're going to interchange the diagonal entries. So 6 and -1 change places. And then the off diagonals, we change the signs. We leave them where they are. So 2 gets to be -2, 1 gets to be -1. I should actually calculate the determinant of P. The determinant of P is -6 minus 2, so that's -8. So we have a 1 over -8 times -1, -2, -1, 6. I don't generally find a whole lot of value in multiplying the -1/8 through, or whatever the 1 over the determinant is, but you can. I think I will here, actually. Yeah, I will. So that's going to be positive 1/8, positive 2/8, which is 1/4, positive 1/8, and -6/8, which is -3/4. There's your P inverse. Okay, we're almost there. So we can say that the 10th iteration of our population is going to be, I'm just going to write the general formula first. It's P D, sorry, D to the 10th, apologies. P inverse times your N naught. So writing it out in all its glory, we get P, which is 6, 2, 1, -1. We get D to the 10th, so 3, 0, 0, -1 to the 10th power, which you could immediately bring that into there and say it's 3 to the 10th, 0, 0, -1 to the 10th. And then P inverse, which is 1/8, 4th, 1/8, -3/4, -3/4, and then N naught, which was 180, I believe. Yeah. And technically, this answer is the correct answer. We are going to multiply it out to see a couple things, though. And there are a couple things to see. So we should do it that way. Okay. Question. Yeah.
Again, the matrix.
So the matrix P, the columns are the eigenvectors of our original matrix A. Yeah. So D has to be the matrix where the diagonal entries are the eigenvalues of A, and they have to be in the same order as the eigenvectors they correspond to. So V1 goes there, lambda 1 goes there, V2 goes there, lambda 2 goes there. You could change it, right? We could have done the matrix where the first column was 2, -1, and the second column was 6, 1, but then D would have to be -1, 0, and 0, 3. But as long as you're consistent, you can write it either way. Okay. So now, yeah, so I'm gonna do this slightly differently than what my handout is showing here because I want to show you something important. So if we multiply this out, we're gonna kind of work from right. It's always easiest to multiply your 2x2 by your 2x1. So if I was actually multiplying this all the way out, I would do this times that first, and then this times the result, and then this times the result. And I probably will do that, but I'm going to show you something else along the way here. So let's do this part first. So we're going to get 6, 2, 1, -1. We are going to simplify this. This matrix is going to be 3 to the 10th, 0, 0. And -1 to the 10th is just 1. So if we're lucky enough to have 1 or -1 as an eigenvalue, you should just say whatever it is to a power is either going to be 1 or -1, depending on the sign and whether it's even or odd. But then this here, we're going to get something we have to calculate. So you get 1/8 times 100 plus 1/4 times 80, which unfortunately is a fractional number. 1/8 of 100 is 12.5. 1/4 of 80 is 20. So we get 12.5 plus 20, which is 32.5. Similarly, 1/8 of 100 is 12.5. -3/4 of 80 is -60. So you get 12.5 minus 60, which is -47.5. Okay. So now here's the part that I want you to see because I do think it's kind of worthwhile. So we're going to do one more multiplication here. So we're going to get 3 to the 10th times that, 1 times that. So I'm going to get, let's do this, 6, 2, 1, -1. And then you're going to get 3 to the 10th times 32.5 plus 0 times that. So let's just write that as 3 to the 10th times 32.5. Actually, I usually write it in the other order. It doesn't really matter, but well, there's a reason. And then 0 times that plus 1 times that is going to be 1 times -47.5. And now I really actually don't want to multiply out this last part. And then we'll say why in a second here. But if we did, yeah, I'm going to do it, but I'm going to show you how I'm actually going to break it down. So if we multiply this out, check it out. We get 6 times that plus 2 times that. So we have, yeah. I'm going to, so watch how I write this. I'm going to get 32.5 times 3 to the 10th times 6 plus -47.5 times 1 times 2. And then similarly, this row with this column, I'm going to get, and I am writing out in this order for a reason that is specific. This times that, so 1 times 3 to the 10th times 32.5 is 32.5 times 3 to the 10th times 1 plus, and then -1 times the second thing here is going to be our -47.5 times 1 times -1. Okay, that looks terrible. Absolute garbage, really. But here's what I actually wanted to do. What I really wanted to do was to write this in the following way. I'm going to write this as the first part as, check this out, 32.5 times 3 to the 10th times the vector 6, 1. Plus, the next part is -47.5 times 1 times the vector 2, -1. And this specifically, if you look at question, let me see in the textbook here. You look in section 8.8, if you look at like question 15 or 20, the problem says express the solution in terms of the eigenvectors and eigenvalues. This is what we have done. Look at this. This is equal to 32.5 times the first eigenvalue to the 10th power times the first eigenvector plus -47.5 times the second eigenvalue to the 10th power, right? That's -1 to the 10th times the second eigenvector. That is what they are asking you to do in problem 15 and 20. I don't think writing it out this way is super useful or informative. Writing out this way is super duper useful and informative. And by the way, you're going to see this version of it in 17C. This formula, something times lambda 1 to the 10th times your first eigenvector plus something times your second eigenvalue to the 10th times your second eigenvector, is where we're headed next quarter or whenever you take 17C. So that's why that's why I think, like, I was wondering if he was going to assign problems like that. He did. So I would definitely, take the time with those problems to write it that way, because that's what we're going for. let's see. But then you might actually want to like so this is nice, but it actually doesn't say what the numbers are. So we actually go back and see what the numbers are. I mean, they're kind of gross, right? Like, I don't know what 3 to the 10th is. It's something. So I actually don't want to calculate numbers. I'm going to leave it like that. Excuse me. I don't think we need to talk about that. So questions about this example? Yeah.
So you said when you call it iterated matrices,
Right. This is iterated matrix multiplication. So it just means repeat it. You're doing it again and again and again. Okay. Let's see other examples. I feel like we should do another example because they're kind of gross. Let's look over here. Yeah, that one's good. Sure. Yeah. Okay, so to break it down, when you're doing this process, here are the steps. Step 1, find eigenvalues of A. Step 2, find the eigenvectors. Step 3, P equals the matrix where the columns are the eigenvectors. D equals the diagonal matrix where the eigenvalues are the diagonal entries. Step 3. Step 4, find P inverse using the usual 1 over the determinant of P, and then the usual switch those things, negatives up here. And it looks real super formal there. You switch the diagonals and you change the signs of the off diagonals. And then finally, maybe not finally, step 5, A to whatever power you need it to be is equal to P times D to that power times P inverse. And then, so sometimes they'll just ask you to write A to a power, right? And you're actually not multiplying it by some 2x1 column vector. They usually are. So then I would say you can go further. And if we are calculating like A to the T times N naught, which is equal to P times D to the T times P inverse times N naught, what this ends up breaking down to, which is kind of cool, I think, is this ends up equaling some constant times lambda 1 to the T times your first eigenvector plus some other constant times lambda 2 to the T times your other eigenvector. And if you really care, the constants C1 and C2, you just get them when you do this first multiplication. That's equal to whatever P inverse is times your N naught. I know I've written this in the weirdest way possible. Sorry. So that's right. If you look back at the problem we just did, and I'm gonna cover this up for a second, I'll uncover it. Right, when we did your P inverse times N naught, we got the 32.5 and the negative 47.5, and those ended up being the constants in the way we wrote this out in the final kind of format here. So those constants come from that first multiplication. All right. So let's look at a couple more examples. Yeah. Sure.
I have a quick question.
Yeah, go ahead.
The other equation, I think it was AD equals PD. When does that come into play? Or is that
So
just...
we used it, but then we moved away from it real quick. So
Oh,
we
okay.
we used it right at the beginning, or close to the beginning. Come on. So I would say it's AP equals PD. So we had that equation, but then we almost immediately multiply both sides on the right by P inverse to get the A equals P times D times P inverse.
Oh, okay. Thank you.
That's the more like useful version of that equation. And again, I'll just remind you, this equation is just coming from the fact that you're really just saying that the matrix times the vector equals the eigenvalue times the vector, and you're just writing it twice for each eigenvector, or one, I should say once for each eigenvector. So let's look at another example. Let's look at maybe an easier example. At least, well, so we want to press the solution to the, I'm going to write this in the most annoying way possible, to the recursion n sub t plus 1, the population at t plus 1 equals a times n sub t, a times the population at time t, in terms of the eigenvectors and eigenvalues of A, assuming 1, that n naught equals 1, 1. So if you don't have to think juveniles and adults, but if you were, you would say we're starting with 1 juvenile and 1 adult. And the matrix A is the very, very nice matrix 2, 0, 0, 1. This problem almost feels like a crime because we're going to do work that we don't really need to do. Because I would point out that A is a diagonal matrix already. And if you happen to see that and you're asked to do this kind of thing, I would say you should probably skip the work we're about to do. But let me show it to you anyway. So, oh, by the way, so first let's address this. So this recursion here, nt plus 1 equals a times nt. So here's what that means. The next, oh, wow. The next vector, the next time vector, is equal to a times the previous time vector. But then, watch this. That's a times, well, n sub t, the number of the population size at time t, is equal to a times n sub t minus 1. And then that's a squared times n sub t minus 1. But then you can do that again. That's equal to a squared times a times n sub t minus 2. That's going to be a cubed times n sub t minus 2. We're kind of just going back in time here. And so if you keep doing this all the way back down to the 0th one, you would have multiplied by a t plus 1 times. So doing this all the way down to a n sub 0, you're going to get a to the t plus 1 times n sub 0. This is just a more annoying way of saying the usual thing, that n sub t is equal to a to the t times n naught. Or in this case, n sub t plus 1 is equal to a to the t plus 1 times n naught. But basically, however many generations from the initial population you want to get to, you just multiply by a that many times. So very, very generally, we're going to say that, of course, why do I always want to write the a first? That n sub t is equal to a to the t times n naught. So if you see this, you should think this, because they really do mean the same thing. Okay, so here's going to be the annoying part where we do more work than we have to do. Okay, let me ask everybody. If this is my matrix, what are my eigenvalues? Show me on your fingers. Use 2 hands. Right, they're 2 and 1, because it's an upper triangular or a lower triangular. It's actually both upper and lower triangular. So my eigenvalues are lambda 1 equal to 1 and lambda 2 equal to 2. Normally I would say that lambda 1 is the bigger one, but it seems like it'd be really annoying to say that lambda 1 was 2 and lambda 2 was 1. That seems like it's ripe for confusion. So let's just be smart about it. So let's find the eigenvectors. So for lambda 1, we're going to find the eigenvector by doing a times v equals 1 times v. So we're just solving 2, 0, 0, 1 times the unknown vector we're trying to find equal to 1 times that. Okay, so look what we get here. This is where things get a little bit weird. If you look at the first equation, you get 2 times x equals x. Whenever you see different multiples of the same thing equal to each other, the only solution is going to be x equal to 0. Or you could literally subtract x from both sides and get x equal to 0. And we need to know, you need to feel it in your soul, that if one of the things is 0, the other one gets to be whatever you want. And but we always pick 1. So if one of them is 0, the other one has to be 1. And pick one. You could, I mean, you could pick like 5, but like pick one. What can't you pick? You can't pick 0. So here our first eigenvector v1 is going to be x is 0, y is 1. And in a similar way, we're going to find v2. So we're going to have 2, 0, 0, 1 times xy equal to 2 times xy. Now we're using lambda 2 equal to 2. You're going to get 2 times x equals 2 times x, which doesn't help, right? If 2x equals 2x, we don't know anything yet. No help. It doesn't tell you that x equals 1 or x equals 5 or that y equals 0. Although in this case, we will get y equals 0. That doesn't always happen. Your first equation can be no help, and your second equation can tell you like 3x equals 2y, and then you get the whatever vector you get. Why did I subtract? So hold on to that question for just 1 sec. So here, looking at the second equation, 0 times x plus 1 times y equals 2 times y. So in this equation, this is going to tell me that y has to be 0. Because if I subtract y from both sides, 1y minus y is 0, 2y minus y is y, I get y equal to 0. Which is the same reason why over here, to answer your question, y subtracted negative x or y subtracted x, because I chose to, right? I want to get 0 on the right-hand side. So I subtracted x from both sides. 2x minus x is 1x. X minus x is 0. I could have subtracted x from both sides and still gotten the same result. I could have had 2x minus x on the left, or sorry, I could have done 2x minus 2x equal to x minus 2x and gotten 0 equals negative x, but that still tells me that x is 0.
I have another question.
1 second, just 1 second.
Okay.
So I would say very, very generally, if you see something like 3x equals 5x, 7x equals 2x, if you have different multiples of the same thing equal to each other, the only way that's true is if that variable is equal to 0. Okay, go ahead.
In this example, vector 1 is 0, 1, but it's written on the right side, whereas previously we had vector 1 on the left side of the matrix.
So when we are, I didn't write. So oh, I see what you're saying. So it is a coincidence that this vector 0, 1 happens to be the same as the second column of our original matrix. But that is a coincidence. It's not that I'm writing. I haven't written the matrix P yet.
Oh, okay, thank you.
So now we're going to write P, and it's going to be super unexciting because look at what P is going to be. P is going to be, well, here's where you might make a choice. Oh, sorry, I didn't finish writing my second vector. Apologies here. My second vector, if y is 0, x gets to be 1. So my second vector is the vector 1, 0. And if it were me, I might make the choice to write my my matrix P as the second vector first and the first vector second, because then it would just be the identity. But fine, we won't do it that way because you probably wouldn't actually do that. So P is the vector, sorry, the matrix where the first column is 0, 1, and the second column is 1, 0. D is the matrix of eigenvalues on the diagonal. The first eigenvalue was 1. The second eigenvalue was 2. And then finally, P inverse, we're going to find it. You're going to switch switch the diagonals. Okay, no excitement there. The off diagonals change signs. But we also have to divide by the determinant, and the determinant is 0 minus 1. And 1 over negative 1 times 0, negative 1, negative 1, 0 is just 0, 1, 1, 0. This is a unique case where P happens to be its own inverse. It doesn't happen very frequently with matrices, but it does occasionally happen. Okay, so now here's the unexciting result. We have that A to the T equals P times D to the T times P inverse, which is equal to 0, 1, 1, 0 times 1 to the T, 0, 0, 2 to the T. I'm bringing that T through already, times 0, 1, 1, 0. I want to simplify this before I actually multiply it by the thing because this one is special. And I really should show you that we could have avoided all this one if we made the observation that A itself was a diagonal matrix. So we multiply this through, look what happens. 1 to the T times 0 plus 0 times 1 is just 1 to the T, which is 1. 1 to the T times, sorry, let me do that again. Sorry, I said something very wrong there. 1 to the T times 0 plus 0 times 1 is what? Something times 0 plus 0 times something? Better be 0. Be careful with your matrix multiplication. It's easy to get distracted and make a mistake. 1 to the T times 1 plus 0 times 0 is just 1, or 1 to the T. 0 times 0 plus 2 to the T times 1 is 2 to the T. And 0 times 1 plus 2 to the T times 0 is 0. And then if we multiply this matrix by that, you're going to get 0 times that plus 1 times that. So you're going to get 2 to the T. And then you get 0 times 1 plus 1 times 0. And then 1 times 0 plus 0 times that. And then 1 times 1 plus 0 times 0. This shouldn't be surprising because A was already diagonal. So if A is equal to the matrix 2, 0, 0, 1, then we should have known that A to the Tth power was going to be 2 to the T, 0, 0, 1 to the T. So again, I will say, I don't imagine you'll actually be given a diagonal matrix to do this process with, but if you were, I just, well, I'm skipping it's probably the wrong choice because you should know what's going to happen. Good question.
Why did the T drop?
Because what's 1 to any power? Right. You could certainly write it as 1 to the T. It would be perfectly fine to do so. We just often don't because we don't need to. So then going back to kind of what we were saying before, if we wanted to express the solution as in terms of the eigenvalues and eigenvectors, so I should point out, that's why we're really doing this work. If you just wanted to find out what A to the T times your original thing was, you could just do that. But this problem was very specific and annoying in that they said, write the solution in terms of the eigenvectors and eigenvalues. So instead of doing this times 1, 1, right? So this A to the T times n naught, which is equal to 2 to the T, 0, 0, 1 to the T times 1, 1. Although it's going to be correct to say that this is 2 to the T times 1 plus 0 times 1, and 0 times 1 plus 1 times 1. This is not answering the question in the spirit of how it was asked, right? That doesn't look like eigenvalues and eigenvectors added together. So what I should have done is I should have not gotten so far ahead of myself and said, okay, well, let's go back. It's still going to be the same. It's just going to look a little different. So we're going to go back to this. We're going to say that A to the T times n naught is equal to P D to the T P inverse. And by the way, the reason I'm kind of harping on this particular aspect is because I would imagine he'd ask something, right? That's really why I'm doing these examples, is because I think he would ask the question where he asked you to write your solution as eigenvalues times their eigenvectors plus eigenvalues to their eigenvectors. So let's do that here. So we're going to get 0, 1, 1, 0. 1 to the T, 0, 0, 2 to the T, 0, 1, 1, 0 times 1, 1 seems like such a boring choice. Okay, so we do this part first. 0, 1, 1, 0 times 1 to the T, 0, 0, 2 to the T. And you multiply that together, you get 1 plus 1, or sorry, we get 1, 1. Not very exciting. And then instead of multiplying out the rest of it, well, yeah, I am going to multiply out the rest of it, kind of. this is going to be equal to 0, 1, 1, 0 times, this I'm going to write as 1 times 1 to the t, 0, 0, 1 times 2 to the t. I know I don't need to write it that way, right? It feels real dumb to write 1 times 2 to the t, but trust me. And then I'm going to point out that's your v1, that's your v2, and we're going to write this as 1 times 1 to the t times v1 plus 1 times 2 to the t times v2. Which, if you look at the work we did before, is literally the same answer, just written out kind of terribly, right? You have, if you actually add these together, you would get 0, 1 and 2 to the t 0. And then you add those together, and you'd exactly get the vector 2 to the t 1. And I would point out that this solution amounts to finding that a to the t times n naught is equal to c1 lambda 1 to the t times v1 plus c2 lambda 2 to the t times v2, where again, c1 and c2 are the result of multiplying p inverse by n naught. Which I should point out, I think he wrote like in one of his announcements that like you're responsible for everything up to the page like 552, very specific. And that kind of idea shows up on page 549. So yeah. Good times. I will point out, it's not that terrible. I know it feels kind of terrible, but it's a process, and you know the steps of the process. Eigenvalues, eigenvectors, P, D, P inverse. Throw it into the formula. What time is it? It's 10:02. Okay, so should we do another example or should we do something else? Is there anything else to do? Like, is there something else I'm totally forgetting about talking about that you all need me to say something about? Doesn't seem like anything's springing to mind, which is fine. This is diagonalization. This is so I will point out that we haven't said the words, but literally A equal to PDP inverse is diagonalization. This is the process of diagonalization. Sometimes for some reasons, you could also point out that you could say that if you multiply on the left by, so you could say that A times P equals P times D, and then P inverse times A times P is equal to D. Sometimes people use that version of this formula for whatever reason. We should not be really. Yeah, we're already doing that. Right, the whole all today has been dedicated to diagonalization. Now we've said the word. And again, the reason that diagonalization is nice is because it allows us to raise a matrix, a square matrix, to a power in, I guess what I say is the easiest way possible. Still not easy, but certainly easier than actually trying to multiply A by itself 10 times or 15 times or 1,000 times. There's another word I want to say here. No, I guess not. Let's look at one more example. And then, so let's say we're given, yeah, we'll do it that way. So let's say that we're just dealing with the matrix here. So we're given the matrix A equal to, what do we got? Oh, I like that one. Sure. Sorry, I'm just trying to pick something that's not like super gross. Yeah, we could do that one. Let's say that A is the matrix. Sorry, I'm very ambivalent, or not ambivalent. I just don't want to make a gross choice here. I guess we can do that one. So let's say A is this matrix. It's the matrix. I picked this one a lot. All right, let's think for a second. 5 minus. Sure. Work out. No, that's wrong. Sorry, apologies. 5 minus. I want a 1 here. I think I've used this matrix before. No, fine, that's fine. Okay, try again. Sorry. Very dramatic. I think we want a 1 there and a 1 there. 5 minus 1 is 4. Yeah, seems right, I think. Sure, that probably will work out. Okay. So we want to find a to the 100th power. Or I should say, find an expression. Which, if you wanted to be pedantic about it, you could be like, well, a to the 100, there you go. But okay, we know what we mean. So find an expression that we could kind of calculate. So, usual steps. If you're being asked to find a to a power, you know you should start off by doing what? Eigenvalues, eigenvectors. So, determinant of a minus lambda I equals 0. I think it's worth writing that down so they can see that you know what you're doing, and then writing down determinant of actually what a minus lambda I is. So 2 minus lambda, 1, 1, 3 minus lambda. I don't think you need to show more work than that. Determinant is going to be 2 minus lambda times 3 minus lambda minus 1. I'm a little worried about my choices here. I'm actually very worried about my choices here. Something stupid. I think I did. Well, we'll find out here. We might abandon this problem if I've accidentally made something that's going to be awful. So we've got lambda squared minus 3 lambda minus 2 lambdas minus 5 lambda. Yeah, plus 6 minus 1 is terrible, James. What did I really want to happen here? I really wanted, oh, that's terrible too. Sure. So I'm going to change the numbers of my matrix, which I know is terrible. I want to make this a 3, sorry, and this a 4. So that really we have that minus 12 instead of minus 1. So then now our polynomial will factor. I would say in general, if you're doing this on an exam and you happen to get something that doesn't factor, double check your work. Like make sure you've actually gotten your determinant correctly, or I should say, yeah, you're this minus that correctly, because maybe you're off by a sign or something, but not that they always factor, because they certainly don't. But on an exam, usually people are not trying to grade something heinous. They're trying to give you something that's going to work out relatively nicely. God, I remember one time for my upper division linear algebra class, someone like halfway through the exam was like, I wrote the wrong matrix. And like the whole exam was based on, we started with that matrix and found like eigenvalues, eigenvectors, all this stuff. Then everything was like imaginary and terrible. And then halfway through, my professor was like, oh no, I made a mistake. It was not great. He said you either keep going with it or do it with the new matrix. So yeah, I don't actually remember what I chose to do, but yeah, good times. So eigenvalues, we found them. Lambda 1 equals 6. Lambda 2 equals -1. So then find the eigenvectors. Okay, so I want you to write down the equation to find the first. So for lambda 1 equal to 6, write down what you need to write down to find that eigenvector. I'm getting the eigenvector as 3, 4. Your eigenvector should be a multiple of that. So just to walk you through the work, matrix times the eigenvector equals 6 times the eigenvector. We use the first equation because we can. 2 times x plus 3 times y equals 6 times x. Good question. I'll get there in a second. Subtracting 2x from both sides because you typically want to get all the x's on one side, all the y's on the other side. So 3y equals 4x. You could go further here, but you don't need to. If 3y equals 4x, I'm going to make the easy choice. You should make the easy choice here. If x equals 3 and y equals 4, then it's certainly true that 3 times 4 equals 4 times 3. So that's one possible choice. Someone asked, why don't you solve for y to get y equals 4/3 and x equal to 1? Because I don't want fractions. You could do that, right? You could certainly say y equals 4/3 x. And you could pick, although I think it's I don't say it's wrong, but it's the less nice choice to pick x equal to 1 and get y equal to 4/3. If you solve for y, great. I would still say pick x equal to 3, and then 4/3 times 3 is y equal to 4. Sometimes people get a little confused because they look at this and they think that the x and y should be whatever their coefficients are, but they actually switch. The y coefficient is the x value, the x coefficient is the y value. That's the way I always see it. In a similar way, we can find the other eigenvector. So for lambda 2 equal to -1, same deal. Matrix unknown eigenvector equal to eigenvalue times unknown eigenvector. First equation, 2 times x plus 3 times y equals -1 times x. Subtract 2x from both sides to get 3y equal to -3x. I wouldn't make my vector 3, -3. I would divide both sides by 3 or just pick 1 and -1. But if I divide both sides by 3, I get y equal to -x. And I would make my second eigenvector 1, -1. Or -1, 1. But I would usually choose for x to be the positive thing if one's positive and one's negative. Okay, the process is the process. Got the eigenvalues, got the eigenvectors. So we have v1 equal to 3, 4. Lambda 1 equal to 6. v2 equal to 1, -1. Lambda 2 equal to -1. And then we can write p and d and p inverse. P is going to be 3. So I know I'm saying this is the wrong way. P is the first column of P is 3, 4. The second column of P is 1, -1. D has entries 6, 0, 0, -1. And finally, P inverse we have to work for. It's going to be 1 over 3 times -1 minus 1 times 4 times switch the diagonal entries, change the signs of the off diagonal entries. So simplifying this a tiny bit, it's -1/7 times -1, -1, -4, 3. I might not choose to multiply the 1/7 or the -1/7 through, but since most of these terms are negative and it's a negative coefficient, I might choose to write it as +1/7 times 1, 1, 4, -3. Not necessary, it just feels nicer to me. It also feels easier to not write all those negative signs. Okay, so now, what we're trying to find, a to the 100th power, something annoying like that? Yeah, okay. So a to the 100th, you should just write it out like this. You should just write is p times d to the 100th power times p inverse. That's worth something, I think. And then we actually write out what we have. So it's going to be p, which is 3, 1, 4, -1. D to the 100th power, and I think we should just raise each of the eigenvalues to the 100th power. That's going to be 6 to the 100th power, 0, 0, -1 to the 100th power, which I would write as just 1. If it was raised to the 101st power, it would be -1, right? Because -1 to an odd power is -1. -1 to an even power is +1. And then finally, 1/7 times 1, 1, 4, -3. Sorry. And then we should probably multiply it all out. So multiplying it all out, we get 3, 1, 4, -1. So here's what I would not do. I would actually, if you have a constant here and you're not doing the thing where you have to like write it as eigenvalue times the eigenvalue to a power times the eigenvector plus the eigenvalue to the power times the eigenvector. You're just trying to find the end result matrix of being raised to the 100th power. I would encourage you to say we can move that constant anywhere you want. Constants are fine to move left, right, whatever. Yeah. And then this matrix times that matrix, so you have 6 to the 100th times 1 plus 0 times 4, great. And then 0 times, oh, sorry, I need to be super careful. This times that, great. This times that, also 6 to the 100th. This dot, I should say dotted, this dotted with that, which is just 1 times 4. And this dotted with that, which is 1 times -3. And then we keep going. You get 1/7 times. Now this dotted with that is going to be kind of gross. This is where things get messy. It's 3 times 6 to the 100th power plus 1 times 4. And then you get, for the second entry here, 3 times 6 to the 100th power minus or plus 1 times -3. 3 times 6 to the 100th power is not 18 to the 100th power. You have to leave it like that. There is no making that nicer. And then on the bottom part here, we're going to get 4 times 6 to the 100th minus 4, and then 4 times 6 to the 100th minus 3. And I do not think you should distribute the 1/7. I would just leave that 1/7 out in front.
Wait, why don't you subtract -4 and then +4 and -2?
So I'm doing the matrix multiplication. So I'm doing this row dotted with this column. So that times that plus that times that. And then this row dotted with this column, that times that plus that times that. And then the second row dotted with the first column, 4 times 6 to the 100th minus 1 times 4. And then this row with that column, 4 times 6 to the 100th plus, and -1 times -3 should be +3. Good call. Since I have 2 minutes, we can also answer the other style of question. So we didn't write it how you did before. Right. So here's why. Because the question didn't ask for that, but also we weren't given an initial population. So let's actually back up. Let's say, what if the initial population was equal to something silly like, I don't know, 20, 30. What is the population 100 generations later? Or in other words, what's a to the 100th power times our n naught? So let's write it out, and let's start from like, sorry, you can't quite see that. Let's start from right here. So we're going to take this, and we're going to write that multiplied by our n naught. So we get 3, 1, 4, -1. Who does that, James? Nobody does that. And then we have, and I will write it out as a combination of eigenvectors and eigenvalues. We need the 1/7 there. Whoop, just sneak in there. In this case, since I'm trying to do the thing, I can't move the 1/7 around because that 1/7 really needs to, right? This here is my P inverse, and you really need to multiply the whole entirety of P inverse by your n naught. And maybe I should have chose multiples of 7. That would have been smart. Oh well, too late. Okay, it's 10:19. Obviously, if you need to go somewhere, you're always welcome to go somewhere. So wrapping this up here, we get these. I'm gonna try to make this a little bit easier for you all to see because I don't want to actually like do too much work here. So you multiply this part out here, you're gonna get 20 plus 30, which is 50 divided by 7. And then this second part here is 80 minus 90, which is -10 divided by 7. And then I really feel like you should jump to the following thing. This is going to equal 57ths times your first eigenvalue times your first eigenvector plus -10/7 times your second, I just back up 1 second. 57 times your first eigenvalue to the 100th power plus -10/7 times your second eigenvalue to the 100th power. I would normally just write 1 there, but I'm trying to be more expressive of the fact that this is the eigenvalue to the power times the second eigenvector. If you actually multiply this out, you would get exactly this. Let me show you. I know it's 1021, but just let me do it, please. So we're getting here 3, 1, 4, -1 times 57 times 6 to the 100th minus 10/7 times -1 to the 100th. And then you can kind of see, oh yeah, look, you're going to get 3 times this plus 1 times that, which is exactly what's happening in the first column. You're getting 3 times 57 times 6 to the 100th plus 1 times -10/7 times -1 to the 100th power. And then the same deal for the second one. All right, I said enough. We don't, oh yeah, I said enough. We'll have a review next week. Date to be determined, Tuesday Tuesday or Wednesday. Please do fill out the evaluation. And good luck on your finals. It's been great. I've enjoyed having you all. It's been a lot of fun. I really appreciated you all coming to class. I like seeing you here. As far as 17C goes, if you, I'm not doing the co-class in the fall, Grant is. So if you're taking in the fall, you'll be with Grant, who is also great. Not to say that I'm great, but if you're taking the summer session 2 is when it is, and we're not super available during summer session 2. So if you're kind of waffling between summer session 2 or fall quarter, and you want more support, I would recommend fall quarter. All right, good luck on all your finals. I hope you all do great. I do have regular office hours today, and then tomorrow we're in drop-in, and the rest of the finals week we're in drop-in. You too. Yes, I have office hours. Well, I have them today, and then tomorrow I'm just available from 10 to 11. And then subsequently during the rest of the week, 10 to noon, 1 to 3 in drop. CD.